I mean, and all of this. If you look at her CV, it's ridiculous how long it is, how many awards she has. So I'll just mention a few. She's a recipient of the National Medal of Technology and Innovation. She was a recipient in 2025 of the Priestley Medal, which is the highest honor that the ACS, the American Chemical Society, awards. She's a member not just of the National Academy of Science, but also medicine and engineering. She's also, I believe, a member of the National Academy of Inventors as well. So not just does she do great science, but she also, I think, has been awarded more than 60 patents. Very recently, from 2021 to 2025, she was actually on the President's Council of Advisors on Science and Technology, PCAST. So she's actually advised at the very highest level on technology and really shaped the way that our government has moved forward on biotechnology. Finally, she is the first American woman to receive the Nobel Prize in Chemistry. Absolutely remarkable, right? So, she's mentioned in the same hushed tones as, I don't know, Jackie Robinson, Neil Armstrong. And it's an incredible opportunity to have her here today. So today, genetic materials, we're talking about making polymers, we're talking about making new materials, even inorganic compounds. She's going to show you all that and more. So just at some point it starts to verge on looking like science fiction, but it's all been published in peer-reviewed literature. It's all true. So without further ado, Professor Frances Arnold.
Can you hear me all right? Super. It's fantastic to be here. It's such a thrill to come up here. I've driven past you all numerous times on the way to Mammoth, and this is this is my first time stopping in. Mechanical and aerospace engineer. At the beginning, well, back in the first fuel crises, oil crises, and I decided I wanted to help the United States wean itself off of oil. So I went into solar energy in the 70s when we had a national goal of 20% renewable energy by the year 2000. Of course, politics changed that when Reagan was admitted. I said, oops, I think I need when Reagan became president, I need a new job. So I went into chemical engineering at the beginning of the biotechnology revolution, when we were just learning how to cut and paste DNA for the first time. So young people, don't be afraid to change fields. It was really good for me. Solar energy went through a very low period for many years, but biotechnology has really taken off. And when I became a graduate student, I fell in love with these amazing molecular machines called enzymes, which are responsible for all the transformations of the biological world. The things that can take abundant renewable materials like carbon dioxide, sunlight, water, and convert that into trees, into you, into me, and make complex, functional, sometimes, materials from very simple things. And enzymes do this. So enzymes, for those who don't get to work with them every day, I'm sorry, but they are everywhere, and the transformations they do just blow the minds of the chemists who study them. They're encoded in DNA. And as a young person, I said, oh, I want to make enzymes, but not enzymes that bind can write any DNA form. Imagine this, you can just type out a sequence of DNA, email it off to your favorite supplier, and you get physical material back in the mail a few days later. Isn't that incredible? You can edit DNA. So my friend Jennifer Doudna, the second woman to win the Nobel Prize in Chemistry in the United States, for gene editing, where you can go in and inside of a living cell, imagine this, you can go inside of a living cell and edit the DNA. So you can read it, you can write it, you can edit it. What you cannot do, and what we couldn't do 40 years ago, and we still can't do today, although we're getting better, is compose it. All right. There we go. We can't compose it. To me, this is the product of 4 billion years of evolution. It's intricate. Even a single enzyme, it's intricate, it's beautiful. It's like a Beethoven symphony, and I'm no Beethoven, nor is anybody else. So how do you compose a new code of life? And not just for enzymes, for all of life. How do you actually sit down and compose this? And this is what I'm going to tell you about today. How do you compose enzymes? Well, what does a good engineer do when faced with a difficult problem? It's hard to compose because these things are incredibly complex. They're really finely tuned. And the structural biologists who thought they would be protein engineers 30 years ago would go in with a hammer and, do protein terrorism, we called it. They never made an enzyme that was better than what they started with. But the process that made them in the first place is, in fact, the process that should be used to make new ones. This was my insight a long time ago now. Think about it. It's an algorithm of mutation and natural selection that's given rise to all this incredible diversity in the biological world. It works at all scales, from molecules to ecosystems. Engineers, eat your hearts out. One process that solves all of the complexity and gives you functional materials and catalysts, human beings at the end of that process. So how can we use this process to go into the future and make future enzymes? Not a new idea. Think about it. We have been using evolution by artificial selection to modify the biological world for thousands of years. We've been making corn, carrier pigeons, lab rats, racehorses. We have been making things that help us in our effort. This pointer is not really good, so I'll use my finger. We've been making things
biologically developed.
Biological, and always there, unless I've done too many energetic materials. Right? We've been making things that give us comfort. We've been making things that are not fit biologically. This, if it got out in my neighborhood in Los Angeles, would be eaten immediately by coyotes. So we've been making things that are not natural, right? But they serve our purposes, and we've been doing it by artificial selection. Now, of course, in the natural world and in the barnyard, you've got some limitations, right? You can go outside and smoke some cigarettes and dial in a few random mutations. You've got recombination where monkeys go with monkeys and worms go with worms, but you're not going to cross monkeys and worms and get anything functional out of it. Certainly not anything beautiful. So the underlying fuel for evolution is very limited in the past. But remember, I just told you that we have all these incredible tools of recombinant DNA. So if you can make any DNA you want, in the test tube, you can make some monkeys and worms. You can have 3 parents. You can have 33 parents. You can dial in any level of mutation you want. So you have complete control over this fuel for evolution. This is Wolford. Wolford is not something we make in the laboratory. Wolford is a figment of Photoshop. He's there to illustrate the power of being able to direct evolution in the test tube. don't make over. He's our exploration of the non-natural world. But think about this. I have all this control now over this process. I choose who goes on to parent the next generation. I can mix the DNA any way you want. I have all this control. That's really good news. The really bad news is we have no idea what the recipe is anymore. Nature already figured out the recipe for natural evolution. I have to figure out the recipe for my kind of evolution. And I have to do that on a time frame of a PhD student, tenure, a few years, and research sponsors who want a result in a few weeks. But before I tell you what that recipe is, and it's really simple, I want you to think, let your minds expand. Because what do we have now? We have the ability to free biology from the constraints of supporting current life, right? Darwinian evolution is she who reproduces fastest goes on to own the world. In my laboratory, it's I decide who lives and who dies, and I can go on beyond where nature really cares about. This is very, very exciting. So we can make proteins or organisms with no natural counterparts. Any biologists in this room? Okay, I'll insult you first. You.
That's procedure.
Biologists think that the whole world of biology is a great place to be studied, and they're trying to understand the rules of biology. But that's the tiniest fraction of the possible biologies. Natural evolution has explored lots of interesting things, but my space as a bioengineer is well beyond that. It's this whole universe of possible biologies. And that's a really big space. Out there, there's cure to cancer. There's the solution to the climate crisis. There might even be the cure to death and taxes. But you have to find it. So in this universe of possibilities, how do you find this beautiful chemistry solution? Let's get back to what we can actually do. This chemistry solution that would be helpful for me. And, some of you like numbers, so I just want to share some of the numbers we're dealing with. When I say it's a universe of possibilities, it's far bigger than the number of particles in the entire universe by many orders of magnitude. And that's just the way you can string together amino acids to make a single protein. So it's an enormous design space. And a protein is typically 300 amino acids long. You've got 20 natural amino acids in every position. Chemists are expanding that all the time. So this is a really big number of possible sequences. Even if you change 1% of the sequence, make mutations in 3 positions, you've got billions of ways to do that. So have any of you read this marvelous short story by Luis Borges called The Library of Babel? Okay, no. I strongly recommend it. It is the best description of an impossible design space that I've ever experienced. He describes the library of all possible books that you can get by randomly assorting the letters, let's say, of the English alphabet. That's a really big library. And in there lies the perfect description of your life from when you're born to when you die. In there is the instructions for owning the world. In there is all sorts of wonderful literature, but it's interspersed by complete gibberish. The vast majority of those books are just gibberish, right? Because it's random assortment of these letters. And so the librarians of this library, which is infinite, are throwing themselves off these infinite balconies in despair of ever finding a single meaningful sentence, much less a piece of literature. And that's pretty much what this space of proteins look like. So here I am trying to evolve into the future, into a space that's mostly empty. But evolution works. So a gentleman code breaker, actually. He's much smarter than I am. He thought about this problem many years ago, and he published a 1.5-page paper in Nature magazine, in which he talked about this evolution, this very problem. How does evolution work in a design space that's mostly empty? And I read this paper when I was a graduate student, and that just gave me so much idea on how to move forward. And here's the thought. Just consider every single protein that exists today, let's say, that you can scrape off the bottom of your shoe. For evolution to work, and he says, I believe evolution works, so that tells me something how these proteins are arranged in this universe of possibilities. Every single functional protein has to be surrounded by other functional proteins in order for evolution to be able to walk through this space one mutation at a time. 2 mutations might happen, but it's so rare that it's not important. Most evolution will happen 1 mutation at a time, and you have to be able to walk through a functional network. He just thought about it. Imagine that. Now we, look to great big databases and proteins to build family trees, and we know that evolution works this way, but he didn't have that. He sat down and he thought about the problem. And he said, this is the way it has to be, and in fact, he's absolutely right. So I can take that in the 1980s and say, okay, I don't want just another protein. I want to actually make a better protein. And so this becomes an optimization problem. And it's an optimization problem on a fitness landscape whose structure we don't know. If we knew the structure, we wouldn't have to go blindly. But we didn't know the structure. And if it's fitness, which is what I'm measuring against all possible sequences, is rugged. If the landscape is rugged, then mutations send you into crevasses of non-function and evolution stops. But Maynard Smith argued that it has to be more smooth in some of its many dimensions, or at least there have to be smooth pathways. And so I translated that into a very simple blind algorithm for directed evolution, and that is randomly mutate and take the first step uphill and keep going. Because if it's Fujiyama-like, any fool can optimize on that. And that really could be done in the late 1980s. We had actually the tools for doing that, where you take the hard part, which is something close to what you want, that you scrape literally from the bottom of your shoe. The DNA for that, you mutate it, but not too much. We're making 1 mutation at a time, more or less. That was easy to do by copying it sloppily under error-prone conditions. Use recombinant DNA technology. The cells would then translate that into mutant proteins. Here comes the good old-fashioned analytical chemistry, folks. I had to search for enzymes that would catalyze a chemical reaction better than its parents, and maybe 1 out of 1,000 would do that. So you have to have a very tight coefficient of variation in your measurements in order to measure the small changes you would expect to get by a single mutation, maybe 2-fold increase in the catalytic rate. But, it really works. And if you can measure that, you can find these beneficial mutations and feed that DNA back into the process and iterate until you've solved the problem. So it looks like this. You start with an enzyme that's really good at what it does in nature. You ask it to do something new. It's generally less enthusiastic. We're all familiar with that. Enzymes are all the same. So it's not very good at what you want it to do, but you can train it through this algorithmic process of mutation and artificial selection, taking small steps until you've reached a new local maximum, and it hopefully will do the job that you wanted it to do. So that process worked really well, and already by the late 1990s had been applied to all sorts of problems. All the enzymes in your laundry detergents have been optimized by directed evolution, because what self-respecting enzyme wants to work in your laundry machine? with surfactants and bleach and everything else. They don't. But they were evolved to do that, and that's why you can wash your clothes at cold temperatures and still get good performance, saving a lot of energy. A lot of your pharmaceuticals are now made using enzymes because instead of a 17-step chemical process, enzymes can bring that down to 2 or 3 steps and even work together in a single reactor, much like a cell. And a number of other industries use enzymes. They're embedded in all sorts of products, from the reagents for your DNA sequencing to things in foods and pharmaceuticals and agriculture and pharmaceuticals. And I'll just share, since I know that biofuels, one of the first applications that we did way back in the 1990s was to make enzymes to make non-natural biofuel precursors. So we developed a process for making isobutanol instead of ethanol, arguing that ethanol was better for drinking and isobutanol was better for driving. That we could make it in in an ethanol plant, and that became the basis of GEVO, which went public in 2011. And I'll just point out, we were the first to fuel a Black Hawk helicopter all the way back. I think this was announced in 2009 or something like that. So we could actually make fuel for, no, I think it was 2012 or so. Yeah, and so that was a real success. You can't make money doing it. You can make all sorts of things with enzymes. It's very hard to make money doing this because when this process was developed, the price of oil was here and the price of corn was here. Now they're different, and so that's not a good economic, but the technology is excellent. So all of that got me the greatest accolade of my life. When I was asked to go down the hall, or down the street to Burbank, in the Warner Brothers studios in Burbank, and play myself on the Big Bang Theory. And I know you are a bunch of nerds, so most of you have watched the Big Bang Theory. If you haven't watched it, it's a very nerdy TV show about graduate students in physics at Caltech who go on after 12 seasons to become extremely annoying professors who are lobbying for Nobel Prize. So my role on this show was to take Sheldon's bribe of oatmeal raisin cookies and throw it with disgust into a trash can. But that was really a lot of fun. I was the first woman ever to play herself on that TV show. They had lots of men cameos, but they never had a woman until the 12th season. But that was good. I also got invited to a great party. Oh, I tell you, Stockholm in December can be cold and miserable, and this is 3 in the afternoon, but it's all lit up for this party for science, and they do such a good job. I have to say, if you ever get invited to this party, you have to go. You just drop everything and go. It's really worth it. All right, so what did we learn? What did we learn by evolving all of these enzymes? We learned that proteins will adapt by a simple optimization strategy. It's almost mind-numbingly stupid optimization, but it works really well. And a lot of people argue, oh, you need more numbers, you need more this and that. This works beautifully. Not for everything, but it works very well. New functions. We didn't know how many mutations it would take. If it took 100 mutations to get useful functions, then I would not have survived because that would have taken too long and I would have not gotten tenure. But it turns out that you only have to change a very small fraction of a protein sequence in order to acquire useful new functions. And anybody who studies antibiotic resistance knows this very well. And then finally, for the would-be Beethovens, so if any of you are interested in computational protein design, and you want to do it in physics-based models, I'll just point out that beneficial mutations can lie 20, 30 angstroms away from the active site, many amino acids away. And even when we have the answers, reverse engineering how they do what they do is almost impossible. Remember, these effects are subtle, fraction of a kcal per mole. We're looking at 2-fold changes in activity, and nobody can explain them, much less predict them a priori. So if you want to be Beethoven, you have to be able to predict beneficial mutations, and that we're still a long ways away from doing. All right, so we have this wonderful optimization strategy for evolution. Starting about 15 years ago, I got tired of doing the same thing over and over again, and I got annoyed by people like the most recent Nobel laureate in chemistry, David Baker, who would sit down and design enzymes thinking he was Beethoven. They were terrible enzymes, absolutely terrible, but they could do chemistry that biology had thought about. And then he would do 7 rounds of directed evolution in order to get it published. And it annoyed me. I mean, it really annoyed me. So I said, for many years I said, oh, I can't do that. I can't get a whole new function. Because if you think about an enzyme and a catalyst, what you have to do is position multiple functional groups simultaneously in order to lower the transition state for a chemical reaction. And I just told you we're taking one step at a time. We can't create a whole new active site by one step at a time. And then I realized I was thinking about this problem all wrong. Because, well, nature is making new enzymes all the time. And she doesn't sit down and design them. She does not use physics-based design to create new enzymes. She uses evolution. So what is going on there? Well, to make a long story short, I'll give you one little example. Atrazine. Here's a potent herbicide that we're dumping onto the planet. And at first it was non-biodegradable. But then some enterprising organism figured out that if it dechlorinated atrazine, popped that chlorine up, it had a new rich nitrogen source that it could use, that it could eat, and give a selective advantage over its neighbors. And so this organism went all over the world and with its enzyme, and all of a sudden, in real time, and I'm talking 50, 60 years, that's real time, this herbicide became biodegradable. Wow, how did that happen? It happened because it was already there. This was such an important lesson to me. Novelty in biology happens as a result of the huge diversity of biology. And also the fact that enzymes can do multiple things. They're kind of like graduate students or interns, right? Now, we don't say that graduate students are promiscuous. We say that enzymes are promiscuous because by virtue of having, all these amino acids and metals and cofactors, they can do chemistry that they were never asked to do before, just at some low level. And if that's the case, then all you have to do is be able to recognize that, and then you turn the crank, just like I showed you with directed evolution, and you can create a new enzyme. Wow. Let me show you an example. This is my favorite example because it shows how you can step beyond where nature has gone. So everybody wonders, why not silicon-based life, or why is silicon not incorporated into organic materials? Because it's pretty abundant. It's the second most abundant element on the crust after oxygen, rocks, right? There are a lot of rocks around. So we've got silicon and oxygen's there, but silicon is not. And so we said, okay, let's make a silicon carbon bond forming enzyme. And for this, we took a little bit of, you have to be able to envision that some natural enzyme would have a little bit of activity for this. So that means you have to know a little bit of chemistry in order to get started. Just like you have to know something about horses in order to breed a racehorse. You have to know something about what might be possible. And nature does this. Nature can take dioxygen and activate it using an iron heme prosthetic group inside of a protein and make a really hot oxygen that it can then insert into a CH bond. And we propose, well, gosh, if that's possible, why not make it, if you squint, right, this carbene, this active carbene to a chemist looks a lot like the active oxygen. And so we proposed, even though there's no carbene transferase known in biology, this chemistry is not known in biology, it's known to human beings, but it's not known in biology, we felt that these iron heme proteins might be able to do this at some low level. And then the question would be, does it evolve? If it can do that, does it evolve? So we tried a lot of iron heme proteins, and a lot of heme proteins will do this reaction at a low level, but one that I particularly love is a itty bitty protein. It's only 100 amino acids long, comes from a hot salty pool in Iceland, and it's so stable, you can boil that thing, and it's still stable. It's so stable you can give it to a chemist. And they won't even know that it's a protein. You just put it in a powder and say, here's a magic powder for making carbon-silicon bonds. Its native function is not catalysis, yet it has a little bit of activity. If you feed it dimethylphenylsilane and a carbene precursor, it will catalyze the formation of a silicon-carbon bond about, on average, 40, 50 times per enzyme. And it does it with beautiful selectivity, better than what chemists had reported. So here's a protein just by virtue. It has nothing to do with its natural function. It just by virtue of having this active site can also do this novel chemistry. Well, that's really cool. But then when I started talking about this, I found this cool protein. I had experts sitting in the front row, and one guy jumps up and says, but Francis, don't you know that a cytochrome C has no active site? He was just dumbfounded that I was reporting it could catalyze this reaction, because if you look at the crystal structure of this protein, you find, and you run your computer ball over the structure, right? You find it has a big fat 0 for the volume of the active site. But you know what? Nature does not care about your calculations. I think it's really important to remember. Your calculations are, our understanding, limited understanding of the physical world. Nature might have a very different understanding, because not only does this protein catalyze that reaction, it evolves. And so we just took it and cranked out 3 rounds of mutation and artificial selection, measuring how much product we were getting out of this reaction. And after 3 rounds, we were 50 times better than any catalyst a human being had invented for this specific asymmetric reaction. And it had perfect enantioselectivity. So it was a really beautiful catalyst, and it used earth-abundant iron, whereas everything in literature was iridium and rhodium, which nobody would want to use. So that after 3 rounds, we knew we could get published in a snooty journal. So we just stopped the experiment and tried to get it published. And then the chemists got in our way because they wanted a substrate scope. So we had to do, 41 new to nature compounds with all their characterizations. So the final paper that got published was 130 pages of supplementary information on new silicon carbon containing compounds that no one in the world cared about, but we had to do it in order to get published. But the cool thing was, this protein not only does all this chemistry, it does it inside of living cells. So it's completely compatible. All these precursors can get into the cells. They've never tried to keep them out. And you can isolate, and for the chemists in the audience, note you can target the silicon hydrogen bond instead of the nitrogen hydrogen bond. So it has perfect selectivity that it learned through the evolution. So when that got published, or actually before it got published, I was talking about this, and Bob Service on Science says, oh my goodness, that's so cool, I need to write about this. And he asked me all sorts of questions, and because we hadn't published a paper yet, I said, I have to zip my lip because you can't publish through press release. So he made up a story we made up a story and said we were taking a step towards silicon-based life. I said nothing about silicon-based life in my talk or in the paper, but this story, because the paper was so boring, chemistry paper, nobody read that. Everybody read this, and the story went all over the world. And not only did it go, oh, and you might notice, you probably can't see it, Spock and Captain Kirk with a Horta episode in Star Trek where they're looking for life in rocks. Actually, we're trying to put rocks in life, which is the exact opposite, but none of that. Anyway, when the story went all over the world and it mutated as it went. So popular science took us to task and said, oh, I don't think so. You know, they might even have a chemist on their staff. And it's true, there are a lot of good chemical reasons why silicon-based life is not possible, even though we didn't talk about silicon-based life. So they said, don't hold your breath. And then when you get to Astrobiology magazine, you know, all 17 readers of Astrobiology magazine clicked on this and made it the more, well, sorry if I'm insulting anybody here, but made it the most widely read article of the year for astrobiology. And then when you get to the intelligent design community, these are the evolution deniers actually. They said, oh, it has to be intelligent design. I said, yes, 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 I am the intelligent designer because I am using evolution. And I'll tell you, the greatest reviews for the paper came from the Twitterverse. The Twitterverse, if you ever want your paper reviewed by humanity, go to the Twitterverse. I don't know if you can read that, but it's not worth reading. Anyway, it had us rolling on the floor with laughter. But I think this really engaged so many people all over the world. It was a great story. But the important thing that I was trying to do with this was open people's minds about what's possible using biology. Because when you open people's minds, you can add new elements to the periodic chart of biology. We added boron and silicon in 1 year to the periodic chart of biology, which really is pretty limited. My colleagues at Caltech can add almost all of these elements to carbon bonds, but not all, but a lot of them, and many more than biology has. And so they used to pat me on the head and say, oh, Francis, biology's cute, but it can't do what I can do. Well, you know, those of you who are thinking that biology is coming after you. All right, my feeling is that if you make things, you should also be able to break them down. And so when Dow Chemical read that paper, they came to me and said, Francis, can you make enzymes that break down silicon carbon bonds? Because here we have products, siloxanes and silicones. You know, there's 50 products in this room that have silicon carbon bonds, all made using dirty human chemistry, and that are accumulating on the planet. They're not biodegradable, and so and some of them are even banned in the European Union. So just last year, we took their money, and just last year we reported the first enzyme that can break carbon silicon bonds. So now we move towards keeping some of the materials we like, but possibly making them one day biodegradable. Once you've demonstrated a new mechanism with an enzyme, you open up a whole new world of chemistry. And for those chemists who love carbines, there's an immense world of chemistry invented by human beings that we could start doing. And then we could also go and make things that the human beings couldn't make. So, you know, bicyclobutane. Let me tell you about that. But we could do cyclopropanes. That works beautifully. I can make any cyclopropane almost that you want. All these insertion reactions. But one thing that I thought I would share with you is that, you know, these carbene transferases can add can make a cyclopropane, a double bond or triple bonds. And so these are transformations, at least to make the bicyclobutanes. They're not known in biology. I already said that, carbene transfer. But they're not known in chemistry either because the selectivity is not accessible or because the catalysts cause degradation of the products as well. But enzymes, by virtue of having this protected active site, can do highly energetic chemistry that would lead to degradation of products in solution. So let me give you this example. We can take an alkyne and make cyclopropenes. Now we've already got 56 kcals per mole of strain energy, so they're pretty hard to make for human beings. But the enzyme, with its iron heme, you give it the carbene precursor, that's the driving force, it blows off nitrogen, and you can cyclopropionate the alkyne to make a single stereoisomer of a cyclopropene. But not only that, you can also convince the enzyme to keep the cyclopropene in its active site and do another cyclopropionation and make a bicyclobutane, a single stereoisomer. So you can evolve the protein to make all the different stereoisomers as well. And now we're up to 67 kcals per mole of strain energy. And now, you can start thinking about making, I don't know, binders for rocket fuels or, other interesting or cores for energetics. So we have a program actually that's funded at a very low level by the US Army to make novel energetic compounds and materials with the idea that if you can have this selectivity, first of all, you could make possibly cores that would be hard to make otherwise, but then you can also make single stereoisomers and we can start looking at some of those properties. Great thing about enzymes, if you could do it at small scale, there's a really good chance you can also do it at large scale under very mild conditions. And so there's some potential cost advantages there as well. So here's what a larger scale reaction looks like. This is Jay Kennemer's work. We took these fibrocycles, for example, are really interesting as intermediates in pharmaceuticals because they have three-dimensional structures. But it's almost impossible to make single stereoisomers of these things. So Jay Kennemer evolved enzymes that work just in the lysate. So what are you doing? You're taking bacterial cells, you're growing up just like you grow them in your refrigerator. You spin them down, you break them open, you spin down all the the garbage, and you have just a liquid lysate, we call it. And that lysate, because it's got this iron heme protein, it's nice bright red. We just add the reagents. No organic co-solvent. It's got a little water in there. You add the neat reagents, and after 10 minutes, you get this nice emulsion. That's the nitrogen flowing off. And then after 16 hours, the reaction is finished, and you can pull out your product. So we can get really good conversions. And we're working at high concentrations, 25 grams per liter of the starting material. This idea that I've shown you, that you can convince enzymes to do completely non-natural chemistry, extends to many other things. And a lot of my former students are doing amazing work in this area. We showed, for example, that you could do the same trick with nitrogen. So if you can transfer carbon, you can also transfer nitrogen using these same sorts of enzymes. That opens up a whole new world of chemistry for making carbon-nitrogen bonds, nitrogen-nitrogen bonds. But I won't. Since the day will get very long if I continue to do that, I will not do that. I'll just point out, and this is an important new area, is this directed evolution is an algorithmic process, very much like active learning and machine learning. And so we can improve this whole process. In the old days, remember there was a trash can there. Most mutations are deleterious, and we would just throw the bad mutants away. Now we take all the data, we get all the sequence function pairs, and we can build machine learning models. And we can empower those machine learning models. If you have neural nets, you can put in evolutionary information, structural information, even your quantum mechanical calculations, and build really good models based on having some data. And you can start your parent proteins with David Baker-like protein design, so you can pick a really bad protein and enhance it with this. And the future is to put all of this together then. I don't, just to demonstrate, the way you speed things up is make multiple mutations simultaneously. Then you get the ruggedness of the fitness landscape that would stymie a directed evolution optimization. But that's no problem for machine learning, because then we'll make multiple mutations and then test small subsets of those and build models in order to capture these so-called epistatic effects. And we can do that with active learning, so you can update the model in each generation, and you can have acquisition functions for choosing which ones to measure that can be steered towards things you think you know about the system. It's very active area of research in my group right now. Half of my group is working on these AI and machine learning versions. I'll also point out every single step in the process. You've got a model, and everything can be automated. Every single physical step in there can be automated. What does that mean? That means that this is what I said in 2022. I said, I decided that directed evolution is finally ready to be run entirely by machine learning. No more painful experiments. Directed evolution is slow and painful if you do it the way we did in the 1980s. But no more painful experiments to get your laundry for enzymes. Grad students and postdocs can just push a button. And so this is one of my grad students came up with that figure, early Dolly AI generation. Now, you may notice the date here, it's April Fool's Day, so I said I may change my mind tomorrow. But it's not an April Fool's anymore. This is really what's happening. So this whole algorithm process will be automated, and I see in the next 5 years that we'll be able to pretty much genetically encode any kind of chemistry. Wouldn't that be incredible? Either through just starting off with design proteins or starting off with things we can find in nature, we can evolve things for pretty much any chemistry. What will that allow us to do? It allows us to take chemists, 150 years of brilliant inventions that they thought, nature had never explored, and marry that with this powerful process of evolution and genetically encode chemistry so that we can use, for example, organisms that know how to use renewable resources already to derive their fuel and their energy requirements and substrates, and use that as the factors of the future to make the compounds we need in our daily lives. Fuels, materials, chemicals, energetics, you name it. We should be able to do that in the next few years. So with that, I will thank you for inviting me up here. It's great to be here, and I'll take questions. Oh, and by the way, I have a lot of really smart people who would, if you need interns or people to, talk crazy ideas with, nice to talk to you.
Professor Arnold,
Francis.
that was absolutely fascinating. Earlier in your lecture, you mentioned that you have to have a continuously functional sequence of actions so the path it takes to get to the environment and
But the machine learning gets around that. Yep.
we found in digital models of evolution, so in computation, that representation is dead code. In other words, code that isn't expressed. In other words, there's code that isn't expressed in order for a potentially beneficial mutation down the road,
Yep.
not to break it now.
Yep.
You see the same thing?
Absolutely.
in
Yeah.
things like that.
I think the parallels are very clear. So there's a lot of neutral evolution where you can just make changes and it doesn't hurt you. Luckily, right? Not every mutation. We have lots of mutations amongst us and they don't hurt us. We're still functional. So yes, there's a lot of that. And so is it extraneous? Is it dead? No, it's not dead, but it accepts neutral mutations. Sorry, we had one in the back. We make the molecules. Absolutely. It makes predictions of the top 10. We make the top 10, and if what we want is in the top 10, we're really glad. Yep, everything. So directed evolution was all empirical. Before the machine learning, it was all high throughput screening. What we're trying to do is reduce the load of the high throughput screening, so we don't have to screen thousands. Maybe we screen 100. Right? We map the sequence space to look for those big peaks that are outside of our immediate optimization. and then direct the evolution towards those big peaks that we can explore. Yeah, well, of course, all of that literature, reinforcement learning, came well after evolution was in there. What are they learning from evolution? They're learning a lot. What we can learn from those is using those concepts to build better models. Yeah.
I saw there's a picture of like a junkyard, and I'm guessing the idea with that was like, being able to break down things that formerly were biodegradable. Would that be taken in an isolated way, like take stuff and then destroy it, or would that sort of be like, when you're releasing something into an area to help take those plastics, what would that mean from like an ecological standpoint?
Right. Well, those are questions well beyond, does an enzyme do it? But you can have contained systems for biodegradation if you're worried about enzymes getting out into the bigger world. With siloxanes, let's talk specific about siloxanes. Those are kept in open ponds, and you've got dirty water. So, would you run into a water treatment facility where, the enzymes would be contained? But I'll just point out, enzymes are non-self-replicating. So if they're not in organisms, they can be put inside of a reactor and they're not harmful.
Putting in the enzyme loops outside of
Yeah,
you're not like
do
putting
that.
a plasmid into a bacteria.
You could do that too, though, but then you'd have to worry about, recombinant.
Yeah, makes sense.
Yeah. Oh, I've got too many questions here.
I got 2 from the online viewers. Do you get a catalytic behavior out of enzymes? And how easy is it to separate targeted products from the reaction mixture?
Yeah, so absolutely, they're catalysts. And so cyclopropionation, we can get tens of thousands of catalytic turnovers for cyclopropionation. Some of the crazier reactions that we do, we might only get 50 to 100. But I think that all of those can be improved with a lot more work. So, if anybody's interested in a very specific one, we work with companies to develop those enzymes for commercialization. And the second question was?
How easy is it to separate the targeted products
So,
from the reaction?
Sometimes it's super easy. The products crash out of solution, so it's a primarily aqueous medium, which is beneficial, right, because you don't have organic solvents to get rid of. So if you have a hydrophobic product, it often just crashes out, and you can just take that, and that's great. If it's more hydrophilic, it can be a lot more difficult to isolate. Yeah. So anybody who does separations knows all these ins and outs.
Thank you. Oh, what do enzymes do in laundry detergents? So in the old days, you had to boil clothes to get them clean, to get stains out, right? You had to really hot water and use a lot of harsh detergents. Your enzyme-based detergents work in cold water because the enzyme will chew through blood stains, grass stains. They're fantastic at actually degrading those biological materials that stain the clothes. And so you can do it all in cold water, and the energy savings that the world has gotten from low temperature laundry is enormous. Oh no, enzymes are just proteins. They degrade themselves, right? Yeah, enzymes are just proteins. We're dumping proteins into the sewer system all the time. Yeah, they break down. Yeah.
So a lot of your research, it looks like, focused on adding new things to biological processes. But I'm curious if you could just start looking at biological processes that you can possibly engineer without certain elements that are normally found. So for example, the obvious one being oxygen. If you could engineer these sort of biological processes and involve enzymes that would work in oxygen to provide environments.
These all work in oxygen. They don't need any
the oxygen. So the answer is yes. And that's the whole glory of evolution, right? You can train an enzyme to need or not need oxygen. You can train an enzyme to need or not need a surfactant. You can train it to need or not need something, if it's physically possible. Right? Some things are not physically possible or not accessible by this random uphill walk. But we found that, and industry has found this, that's why I got all these prizes, is that industry has found that enzymes can often be trained to do a whole lot of really useful things.
So it sounds like find the environment that you want this to work within.
Make the biology work with you. That was my vision. When as a young engineer, I came into biotechnology, and we were cradling enzymes, for all these things like glucose monitoring and various therapies. We were cradling them because they were so fragile and had to be treated so carefully. And I said, well, that's terrible from a process point of view. An engineer wants something that's robust, that will work, at room temperature. And I said, I want to be able to make enzymes do that. Only had no clue how to do it. And that's where the evolution came in. That's exactly right. And that's why biotechnology, enzymes at least, are really coming to take over chemistry, because the industrial demonstrations of this are mind-boggling, what they can do. Great.
Thank you for joining us today as our second distinguished lecturer. And so we'd like to present this award to you. I'm going to read what it says real quick. So Francis Arnold, PhD, with gratitude for your contributions as a distinguished lecturer, thank you for your commitment to advancing innovation and the Navy Tech Connect mission to connect ideas, technologies, and people in support of the warfighter. Thank you so much for joining us today. We really appreciate you being here.
Thank you.
So please, everyone.
I'll just point out that guy that was in the Black Hawk helicopter on the slide I have is my son in Afghanistan. So I'm all about protecting the warfighter.
For making the award, and please everyone stick around. We have our step and repeat up in the back. Hopefully Dr. Arnold doesn't mind if you take a few pictures with her, and just please network, mingle, enjoy the space while you're here, and thank you again for coming out today. We exist because of you all, so please continue to support this tech.